team leader, and I'm honored to be your MC today. The technology team's mission is to provide accurate and timely information on current and emerging technologies that can improve productivity, competitiveness, quality, and profitability among the NTMA membership. One of the ways we do this is by hosting relevant technology webinars. The topics we choose come from you, our membership. So if you'd like us to cover a topic that's important to you, just shoot us an email, pick up the phone, or type a note in the GoToMeeting chat box. We value your time and promise to start and end on time. If you haven't already done so, please enter your audio PIN number that you received as you signed in. The format is pound, PIN number, pound. This will help us provide the highest quality webinar for all who are attending. This is the second of 2 webinars on 5-axis machining. Both will be posted on NTMA's website in the coming weeks. Whether you are considering adding a 5-axis machine or have been using the technology for years, we want to put a resource in your hands, someone that can answer your questions. And our presenters have a tremendous amount of experience, so please feel free to contact them. In today's webinar, we'll compare and contrast the high speed and high performance aspects of 5-axis machining, and we'll also explain how your specific milling strategy or approach impacts your machine selection. When we are done, you'll have a good grasp on which 5-axis technology is best suited for your specific applications, and we'll offer practical suggestions for optimizing your 5-axis machining processes. We're honored to have Gisbert Ledvan from GF Machining Solutions and Bill Vanovic from Grobe Systems presenting our webinar today. Gisbert completed his tool and die apprenticeship in Germany back in 1983 and has been involved in many different industry-specific roles over the past 23 years. Gisbert moved to the U.S. in 1993, and he is now the Director of Business Development at GF Machining Solutions in Lincolnshire, Illinois. Bill Vanovic is the VP of Universal Machine Sales for Grobe Systems. Bill started his manufacturing career as an NC programmer, and for the past 30 years, he has held a variety of engineering, new product development, and VP positions with several of the major machine tool builders. Currently, Bill guides the development of 5-axis machining centers, automation systems, and software at Grobe Systems in Bluffton, Ohio. Both Bill and Gisbert serve on NTMA's technology team. If you joined us late and haven't already done so, please enter the audio PIN number that you received as you signed in. Again, the format is pound, PIN number, pound. This will help us eliminate any unwanted audio distractions. If you'd like to ask questions, please use the chat box function on the GoToMeeting screen, and be sure to send to all. Our presenters will answer them during our Q&A at the end of the webinar. So without further delay, Gisbert Ledvan and Bill Vanovic on strategy and process optimization for 5-axis machining. Men, thanks in advance for educating us.
Thank you very much, Mike. Welcome everybody, and good morning, good afternoon. We will dive right into our second seminar series on 5-axis machining. Before we go into all the details, we will focus mainly on 2 items today. One is the high-performance machining, and the other one is the high-speed machining. Here I do a little differentiation between the two. And to simplify it, really, if I'm talking about high-performance machining, you really want to focus on removing as much material volume as possible in the quickest amount of time. So that's the formula on the left here. And on the high-speed machining process, you're really looking for covering as much surface finish as you can in the shortest period of time. So that means you have to have a very high speed and feed and acceleration and deceleration rate compared to a high-performance machining process where you're more looking for a rigid machine, a high-torque spindle, and not so much for high speeds. So the high-speed technology is more with high RPM spindle speeds and high feed rates, For example, you would use linear motor technology to achieve that type of application. Now we look at the two strategies. Going back to our first seminar, we were talking about the indexing process, where you basically take the advantage of the 5-axis machine and you basically move your part into a different location, and then you maybe apply a 3-axis motion to cut the part. You turn the part to the other side and you machine another feature. So the machine will automatically index. You can have drilling processes, or you can have a 3+2 application. That means you position the part and then you move 2 or 3 axes at the same time, but you never really use in that process all 5 axes. That is what we're talking about on the right-hand side when we speak about simultaneous machining. There's a picture on an impeller application here where you really use the 5-axis process all the way from roughing to semi-finishing and then to the final finish cut, where you do some flank milling, where you do 5-axis plunge milling for the rough cut, for example. But the big difference here is really that all 5 axes are moving at the same time and preferably at the same speed. If they don't move at the same speed and they're lagging behind each other, then you will have problems with surface quality, with accuracies, and you're going to wear out your cutting tool much, much faster. So it's important that when you talk full 5 axis that you have simultaneous speed in all axes.
And if I can interject on this slide, this is the importance of looking at a purpose-built 5-axis machine tool. You can take a 4-axis and bolt a rotary table onto it and simulate the motion of a 5-axis, but unless the machine is designed from the ground up to take advantage of the simultaneous contouring, that's going to be the claim to fame for this type of machining. The least responding axis is going to control your process. So bolting on a third-party type table typically will slow down the remainder of the axis to maintain path smoothness.
Okay, thanks, Bill. So one other important component, and we're going to go into that a little bit later, is really a simulation software. And we really recommend that you get that if you go into 5-axis machining. And there's different software types out there. In this case, I'm showing here the complete software. That's what we usually use. But there's VeryCut, there's other software versions out there. Important is that you have such software connected to your CAM system so you can do a full simulation of your process before you send the program over to the machine from your CAM system. You want to avoid any type of collision, specifically when you go into full 5-axis. You never know how the motion is going to look like, and you can have collisions very quickly there if you don't verify that program before it goes to the machine. And that's something really to invest into if you invest into a machine tool. So the next slide is going to have a video, and I choose a video what shows a little bit about high efficient, what we call high efficient machining or high performance machining, and the high speed milling process at the same time in the same part. So we're basically starting out with the high performance cutting on a HEM 500U at a 5-axis, full 5-axis machine. This part took about 7 hours to machine. Remember, this is mold steel, so very, very hard material. And here you can see the roughing process. Again, the high performance. The objective here is to remove as much material as quickly as possible to come as close as possible to your final surface area. This particular part is a lens mold for a car, and we're using basically a 5-axis machine, but in a 3-axis motion. As you can see, we're moving only X, Y, and Z, and the table basically stands still in this particular case. So we're really making sure that we're getting as close as possible to the final surface size and remove in the cavities very much material as we can. As you can see here, We're tilting the part so we can use a much shorter cutting tool to have a rigid setup so that the tool doesn't bend on you, and the 5-axis positioning allows us to do that. So we have a short cutting tool. We can remove many more chips. We can apply more power to that, and we can keep the cutting tool itself short and reach very deep into the cavities. So now we're switching over to the high-speed 5-axis fully simultaneous process. So this is a linear technology machine, and as you can see, maybe the video is a little lagging here, but we're moving all 5 axes with, in this case, a 42,000 RPM spindle speed. We have about 1.7, 1.8 G acceleration, deceleration with these linear motors here, and we're spinning the part, we're tilting the part, and that's all in one simultaneous motion to allow you to get the absolute accuracy and the surface finish you desire for this particular part. So I think the picture speaks for itself on this particular case. So you got to really make sure that if you have an application like that, you really have to securely clamp that part. Otherwise, it can spin off your table, and you don't certainly want to have that accident happen for you. So, so the deep cavities, as you can see here, are now finished up in a very fine step overs. And again, this material is probably close to 50 Rockwell hardness. And as you can see here, this is the part as it comes out of the machine. So there's no rework to be done. The finish is spotless and can be used right into the mold if you want to do that at that point. So I'm gonna move on. It's just a couple images here where you see how that particular part was finished up. Okay, so you can find that also on the YouTube video if you're interested on that. Bill?
Yeah, as Gisbert mentioned, tool length and interference is very critical on a 5-axis machine. On a 3 or 4-axis, the programmer can pretty visually prepare on where his tool holder is going to be. On a 5-axis, it's very hard to visualize. So it's critical to keep the interference of your tool, the length of your tool, and the size of your part in consideration at all times. Simulation software is the key to make this work without a lot of crashes in the meantime. Good. This is an example of a part where effectively this part could be made on a 3 or 4 axis with multiple setups, lots of refixturing, and maybe not ideal tool approach to the parts. Also, if you notice in the bottom, we're clamping this part in a dovetail. This is something you may want to consider. You might be making a part today, but if you look at a different way of holding, in this case, we've added maybe 3/8 of an inch of sacrificial material on the bottom, which simply is somewhere to clamp the part, which we just snap off at the end, allowing us to manufacture a complete part in one handling. Very efficient way to make the process.
Okay, good. So here's a little illustration about where we see 5-axis machining becoming more and more important for certain industry segments. And if you not really have seen something like this, this is like what we call a spider graph. And what we're illustrating here is these dot points. The closer you get to the 100%, the more it's used in that particular industry. So if you look on the left-hand side, we're talking about production machining. On the right-hand side, we talk about mold components. And I illustrate this here based on applications we see out there and where we have customers and where customers showing an interest to apply this type of technology and demanding it more and more. So if you diversify your shop and you want to get into some of these industries because they're hot, as we know, last year we sold about 18 million cars in the United States. So that's a pretty hot topic. So 5-axis is becoming more and more important in motorsports and automotive, defense, energy and power generation. Certainly what also then links into the aerospace and aeronautics. You can see almost every part today is machined in 5-axis, either 3+2 or full 5 in the aerospace applications. The parts becoming very complex, and the only way to do that really sufficient and efficient and accurate is with one setup, machining 5 sides of your part or simultaneously. If you're in the mold and die business, clearly, again, automotive to a certain degree, home appliances, packaging, there's still a lot of things what can be done with the EDM process. However, 5-axis is becoming more and more important now in the mold and die market as well.
And to reinforce what Gisbert just mentioned, these are what we feel are the target markets for 5-axis machining. The upper left, rotating as well as structural aerospace parts. Every surface tends to be tilted in some way, any more in an airplane part. The lower left example is a very good example of a 3+2 application. Rock bits for the oil field are a perfect application for this type of technology. It eliminates a lot of setups, gives you a very accurate part in 1 or 2 handlings. The upper right, medical industry. Again, this is a sculptured true 5-axis environment where most parts do require sculptured surfaces. And the bottom right, automotive, again, a 3+2 application. Typically very high volume, elimination of setups and more precision into the parts, less labor by reducing handlings. Medical knee joints. Medical industry is growing, and it will grow as the baby boomers get older. A lot of application here, and this truly is an area where true 5-axis is mandatory. Very specialized type of machinery and very high finish part requirements. Another example of a part that could be done on a vertical or horizontal machining center and multiple handlings. This is a case study where we're able to reduce cycle time throughput by 68% by rethinking the clamping of the part and being able to complete the part in 1 handling. Tire molds are probably one of the most complex true sculptured 5-axis parts out there. This is a growing industry. Unfortunately, most of it is outside of the United States, but we're seeing a lot of development work happening in North America.
So I think not only in the aerospace and in the typical industry we know of is a big change. You also see these shifts now in applications where we talk about consumer goods. And if I can quote here Johnny Ive, who's the Senior Vice President of Apple on the design side, he really found out that it makes a lot of sense to reduce the cost of fixturing by utilizing 5-axis applications or 5-axis machines to reach the part from all sides, improving his production process, making the parts more accurate, get better surface finishes, and maintain a quality they're looking for. So there's a shift even in the consumer electronics industry, and one of the market leaders is applying 5-axis applications in the United States, but also obviously overseas. So one thing I want to get a little bit deeper into it, you have to really look at the particular part. And this is a part what Bill mentioned before, this bearing block. So what we're focusing here on now is really to look at the part itself. If you have a 3D model of it, that's great. If you can print it out with a 3D printer so you have a better view of it, that certainly helps out. Make sure that all the features can be machined on a 5-axis machine, so you can reach in, you can hold the part. You gotta also make sure that you have all the data from your customer. Do you have it as a 3D model? Do you have it on a print? Is this feasible to do in a production environment. Can this part be produced with a full 5-axis or a 3-axis application? Should you do a pre-test before you cut 5 parts or 10 parts because you have some critical dimensions and you want to make sure, even though if you simulate everything, sometimes depending on your cutting tools and your chip flow and how you cool the part and your cooling comes into the part, you might have to make some minor adjustments to get the accuracy you're looking for. I always recommend to talk to the customer, work with him very closely. Like we talked about before, if you want to put some little dovetail areas on the part in order to hold it better with a 5-axis application, you should talk to your customer. Maybe you need to make a little design change, what can save you a lot of time, a lot of reduction in cost of fixtures. Check the data quality. Specifically, if you do 5-axis high-speed machining and you want to get surface quality and you have a lot of details in there, if your quality of your CAD data is not perfect, the machine will actually reflect that. The machine will move that accurate and will reflect all the imperfection in your CAM program, and you will see that on your part. So make sure the quality you get from your customer is perfect, or repair the 3D model so you make sure that you have that. Make sure all the specifications are there. The customer describes exactly what quality, what accuracy is required, so it helps you to set up the part the right way and where you start cutting the part. You might need the 3D files if you have to do a redesign. Don't start and all over to design something. Talk to the customer. Make sure you're going to get the 3D file for your application so you can redesign the part and the fixture if you want to. Also identify the process. Certainly you want to make sure the customer is happy with the results you're going to provide, and if you have to do a sample part for him, do that. What accuracy do you have to achieve? Is it more like a high performance application, or are you looking for a high surface quality? That also depends what machine you choose, what tools you choose. Make sure it's cost effective. I mean, I'm not saying everything has to be done in 5-axis. You can save a lot of time, but there's plenty of other parts out there you might still want to do in 3-axis instead of moving everything around with a 5-axis. But again, don't forget, as I showed you in the video, you can also run a 5-axis machine and operate it in a 3-axis mode. So you can still take advantage of that. Program it away. Get quality tools so you don't have to do any rework on this. This should come right off the machine. The part should be done on the machine, should come off the machine without any additional manual work. So make sure you look at your time management, look at your cutting tool cost. That's another factor you got to figure into this, specifically with 5-axis and high-speed machining. You have to look at that. And make sure you achieve what the customer is looking for, not overdoing it. Make sure that the part is right to the specification the customer is looking for. So how can we do all this? You got to choose the right machine with the right options. If you're in the market to look for a machine tool, certainly you should look at some of our machine tools. However, you got to look at your applications. You got to look at the variety of parts you're going to make. If you do a lot of big machining, you're removing a lot of chips, big material, you want to have a high-performance machine. You want high-torque spindles. You want a rigid machine design. Pick the right tools. Pick the right fixtures. Not every cutting tool is the right tool for a 5-axis application. Same thing with the fixtures. Make sure that you can reach around the part from all sides. The tool holders are very critical, specifically if you have high-speed applications, you have 40,000 RPM spindle speeds, you have to go to an HSK tool holder. So those are things you have to consider that might affect the entire shop to do that. Choose the right CAM system. Don't buy something cheap or is not powerful enough and doesn't have an interface to a verification software, like I said, Complete or VeriCut, what then basically produces a postprocessor and provides the G code you need to run the particular part. Also look at your cutting strategy, like you saw in the video. What are you going to cut first? Maybe there's something you can cut before you go to the full 5-axis simultaneous application. Maybe you can do that on an inexpensive 3-axis machine, hawk out the material, and then take it over to the 5-axis and finish the part there, if you want to do that. So take all that into consideration before you make your decision and buy the right machine tool. One thing I want to show you too, how important it is to have the right cutting tool and the right cutting tool coding on your cutting tools. Here's an example. It's a high-speed camera where we're looking at how the cutting tool looks in the cutting process. So we have two examples here. The first one is a normal HSA tool, what is not coded. And you can see the chip itself really stays a long time on your cutting tool. It warms up the cutting tool and eventually it's going to wear it out. Here's the same shape of the cutting tool, what is coated with a special titanium coating. And as you can see, the chip flows off much quicker off the tool. All the heat goes into the chip, and your cutting tool will last much longer. So it's a critical component of a high-speed milling process to pick the right tools. Maybe you have a solid carbide tool with a titanium coating or any other coatings what is available now out there. So again, just in between to summarize here a little bit. Analyze the part, think about your machining strategy, how you're going to approach it, pick the right cutting tools, make sure you have them before you start putting the part on the machine, because if you have to wait a couple of days to get these cutting tools, you're going to waste a lot of time. It's all about the preparation. Pick the right data, pick the right cutting tools, look at your chem system, and make sure that your post-processing system or your verification system has all the features in there what your high-speed or high-performance 5-axis machine needs to perform well. There are certain G and M codes every manufacturer will have in his machine to outperform and have a very good performance in certain applications. Make sure that that chem system or the post-process system you use will provide you that information and provide that information to the machine before you start machining. Otherwise, you bought a very expensive high-performance machine and your post-processor will not give you the information or data that machine needs to perform at that level.
And on the simulation side, you may already be using something like VeriCut on your standard machines, but the amount of detail that goes into a 5-axis simulation is critical. You want to start with a good 3D model of the machine tool itself, so you know where all the keys, housing diameters, anything that could possibly interfere. You want a very good detail layout of your fixtures and clamps, as well as your tool holders, extensions from the tool holder, anything that could possibly hit. The more detail you put into your simulation, the less risk there is of unexpectedly crashing something at the machine tool.
All right, and then coming a little bit back to analyzing your production plan and analyzing the quality of the tool or the part, what is required by the customer. We pointed this out before. Look at your 3D model. Make sure all the details, all the connections between the different segments are perfectly connected. You have to have a very clean model in order to making sure that all the details are really machined the way the customer in the print describes it or the 3D model describes it.
And this is actually a bigger problem than you would expect. A lot of customer models may have been built up from a 2D print, a part that's been in production for many years, and there's a lot of slop. There's a lot of lines that do not intersect. They look perfectly fine on your CRT, but when you actually try to machine that, if the lines do not actually intersect, it'll either cause an error or a divot in your part. That's very hard to find. So going back and fixing the models and making them accurate, because you can spend as much time as the actual part program, if not more.
That's correct. And look closely to the print. What is required? You know, is it roundness? Is it parallelism? Is it perpendicularity? what is required on every part and every section and every component. That's very critical when you do your 5-axis operation. So you know what is the critical measurement, what is the critical dimension, so you really take that into consideration. And that's when it comes back to what we call the kinematics. And I know some of you were a little bit concerned about this, and maybe I went a little bit quick last time about what the kinematics are. And that's really a key component of your 5-axis machine. Because what you do, or your service engineer will do, or yourself can do, you basically mount a ball, a ceramic ball usually, on the table, on the 5-axis table. You have a probe in your spindle, and then the machine will probe around that ball and determines exactly the pivot point of your axes, X, Y, Z, B, U, V, C. So all the axes you're going to use in the simultaneous application, or even in a 3+2 application. Because if the machine doesn't know exactly at what point the table pivots or rotates, that will influence your accuracy of the part and your hole location and the size of your hole and the roundness of your hole, if you have some features like that in your part. So it's very critical that before you go into a very accurate application, I would always recommend to run the kinematics measuring cycle on your machine, so the machine determines exactly where this pivot point is. So when you run your program, the machine knows exactly where the end of your cutting tool is in relation to the turning point of your A, B, or C axis.
And this is extremely critical. What we discussed earlier, you can build a lot more accuracy into your part by eliminating setups and eliminating handling. It's all based on knowing this true center of rotation. If you had, let's say, a 5,000th error in your pivot point, and you index from the 0 face to the 90-degree face, that 5,000th is going to get calculated back into the part. The other side of the coin is, this may look complex in a 5-axis sculpturing application that would require a CAD/CAM system to produce the part, but knowing the true center of rotation in a 3+2 application, you can simply translate your 0 point to the blueprint 0 in your part and program it off your blueprint longhand. The machine will handle the calculation, the trig required as you rotate the axis to bring the 0 point back to true position.
So look at the quality features of your part and run that through your simulation software. So look at what cutting tools you're going to use. Are you going to use a ball nose end mill, or are you going to use something with a taper on it? As you can see here in these illustrations on the left-hand side, there might be some critical areas where you have a fixture in the way. When you have a deep hole, you're running this through your verification software. And if something turns red there, you have a risk of collision. So make sure you take advantage of that CAM system. But also you can nicely see here that you can reach into deep cavities with a 5-axis tilted part and still using a very short cutting tool. So take advantage of that. And as you can see that here on this part on the right-hand side, we have a very short cutting tool tip here to reach into these cavities. So you can even create sharp corners by utilizing the 5-axis motion on your machine.
Again, kind of back to fixturing. Many parts that are produced on 5-axis machines can be produced on 3 and 4 axis. The key, again, is elimination of setups and reduction in handling. This could take a little bit of rethinking about how you're going to hold the parts. Here's a couple examples of using 0-point clamping, possibly bolted up through the bottom edge of a surface, allowing access to all 5 sides of the part. A little more conventional type of tombstone fixturing. You can still use tombstones depending on your rotary axis configuration. You can stack multiple parts. You can take advantage of the ability to tilt and keep using shorter tools rather than trying to walk down the wall of a surface. Again, just keep fixturing in mind, and maybe you start with a clean sheet of paper and think of maybe the optimal way to hold the part to give you the most access.
And thanks to Big Kaiser at this point, they provided the pictures to this for us, so you get a good idea of what possibilities are out there and how they recommend it and what their customers are using in a 5-axis application to do that. Again, I want to talk a little bit about cutting tools. Please look at everybody out there. Look at, there's so much new technology out there. There's so many new tools available. And you might not use them always in your 3-axis applications, but with 5-axis, you have so many opportunities to reach into the part, around the part, take advantage of these new ball, bull, flat end mills. There are new cutting tools out there with barrel shape, oval form, lens shape. I mean, day by day, there's new stuff coming out, and you can really take advantage of these cutting tools by applying the 5-axis technology with your machine, and you can outperform your competition. You can make parts your competitor can't do if you really look into this and take advantage of these tooling people. They are experts. They see it all the time. Find out what is the best speed and feed rates for these cutting tools for certain applications, for certain materials, and they will help you a lot with selecting the right cutting tools for that. In addition to the cutting tools, it's critical that you look at, for example, there's a VDP chuck. What is a vibration damping chuck? There's technology out there from Systems 3R in this case. Are you going to use oil? Are you going to use a water-based lubricant based on your application? What type of tools you're going to use? Specifically, again, comes down to high speed, 5-axis, super finishes. It might be good to eliminate any type of vibration. So if you have a collet holder, it might be a little bit better than going with a shrink fit. So look at all these options and take advantage of them to apply them to the right technology you're going to use. The other thing I'm just pointing out here on the bottom left, if you think about if you can use a 20% bigger tool diameter, you have about 50% less deviation of your tool pairs. And the same thing is about the tool lengths. Again, 5-axis allows you to have much shorter cutting tools. 20% less on the tools, lengths on the tools gives you 50% better accuracy on your final part and on your final accuracy. Again, a couple illustrations here about your planning process. Look at the part, line up your tools. Make sure you have a large enough tool changer so you have a big pool of tools always available to your application, so your machine is immediately ready to run. As you can see in these images here, where are the critical areas where you could have a collision? Run that through that. Look at all these possibilities to make sure you take advantage of the optimum tool path to reach into your cavities and into your part. Again, when you're looking at high speed and high performance, Bill and I agree on that probably Siemens and Heidenhain are really the strongest controls out there, because you have to deal with a lot of data, and you have to make sure that the data is going through the CNC control very quickly, so that the axis can move simultaneously at the same speed. And those two controls are really the ones where you get that performance. So to summarize this a little bit, look at your process setup, your tool setup, fixture setup, the machine tool itself you're going to use for high performance or high speed. Make sure your maintenance on the machine is done, and that refers back to the kinematics. Make sure you do that once in a while, recalibrate your machine, and then you can execute your process. So in summary, if I look back to both seminars we did so far, we looked at What material are you going to cut? Are you going to cut aluminum? Are you going to cut steel? Are you going to cut hardened steel? Are you going to cut alloys? Are you going to cut titanium? Based on that, you make a determination what cutting tools you should look at, what cutting tools you should buy. Make sure you have the right edge geometry on your cutting tool. Are you going to do high speed or are you going to do high performance machining? That determines also what type of cutting tool. Are you going to use a fly cutter or are you going to use a solid carbide tool? Look at your machine tool. If you don't have a machine tool yet and you want to get into 5-axis, make sure that the machine base is a solid machine base so it can handle high speed. Don't just think if you put a 30,000 RPM spindle on your machine tool, you have a high-speed machine. That machine has to be built from the ground up. You have to have a vibration damping base. You have to have lightweight movement in your axis to maintain the high speed. The control has to be very fast and powerful. Your spindle has to be able to go to 50,000 RPM spindle speeds. Make sure your coolant management is perfect, so you keep a temperature stable environment and a temperature stable cutting condition. On the workpiece side, again, think about your clamping system. You might have to invest in something new. A vise might not always be the solution and the answer for you if you want to do 5-axis. You might have to invest into a zero-line clamping system or be more creative on doing that. Think about automation. That might be something, even a simple pellet changer might help you to be more productive and take advantage of the 5-sided machining. You can put the part in and out with a pellet changer, and you machine the part from start to finish, and you put it back in the pellet changer, and you have a finished part you can deliver to your customer. Don't think about rework. Make sure that your machine is calibrated right, you use good cutting tools, you verify everything, you can get the part of the machine within a couple tenths of accuracy or less than that if you pay attention to the details, and you can deliver really good parts without any manual intervention. Think about your CAD/CAM system, look about the strategy you're going to apply to cut the part, and make sure you control your process in your environment. Also, if you want to cut accuracy, make sure you don't have a garage door open and you have a temperature swing from 10 to 15 degrees. You will see that on your part at the end of the day, specifically if you do 5-axis. It is critical that you have a fairly stable environment, temperature controlled environment, in order to hold that accuracy. Bill, you want to add something to this before we move to the questions and answers?
No, I think we got most of the highlights covered.
Okay. So, Mike, I think we give it back to you.
All right. Great. Gisbert, Bill, thank you very much. Hey, just a quick reminder that both of these 5-axis webinars will be accessible on the NTMA website in the coming weeks. Also want to say thank you to our friends at Big Kaiser for providing of the tooling and work holding slides that were used in today's webinar. Big Kaiser will actually be presenting one of our upcoming webinars on setup reduction and quick changeover. So look forward to that one. Hey, have a couple of questions already in the queue, and if any of our attendees have questions, please send those through the GoToMeeting chat box, and we will get those asked as well. First question, what key components or options are needed on a machine tool to do high-speed machining?
I guess I can start off with that one. As Gisbert mentioned, high-speed machining requires very tight coordination of axis, requires lightweight but rigid componentry. So again, you want to look at a machine that's built from the ground up as a 5-axis, not considered just a bolt-on table. The performance of the axis blending together is the key. You can have the fastest X, Y, and Z travel in the world, but if you have a rotary table that accelerates very slowly, to make an accurate part, you have to detune the linear axis to match the rotary axis. So tuning and accuracy is critical. Along with that, once you're into the high accuracy mode, all of the premium controls have the ability to manage path accuracy. When you're doing roughing or semi-finishing, you can tell the control that you want to maintain, say, plus or minus 5 thousandths. It will overshoot, it will round, but it'll take muzzle off quicker. Basically, just by changing of control of option within the control on the fly, you can take that same path and now reduce it to, say, 5/10 path accuracy. It will automatically slow down at very tight geometries to maintain that accuracy, but will give you a perfect accurate part at the end. So that takes a little bit of experience to manage those parameters, but it can give you very efficient roughing and very, very accurate finishing with no handling, just the change of a G code effectively.
I would say from the option side of, I would always opt in for a large tool changer if you can, because specifically with 5-axis, you want to use a variety of tools to address all the details on your part, and you don't want to be limited to 30 or 60 tools. You might want to go to 100 or 200 tools in your tool carousel to be ready for any type of application. So it gives you a lot of flexibility. I also would say another component is to look at the spindle you have on that particular machine as an option. Make sure you get the spindle speeds, or if you're looking for high performance, make sure you have the torque and ceramic ball bearings. If possible, if you looking for a lot of accuracy, find a spindle what has a cool core. That means the spindle is cooled separately with a chiller to hold the temperature stable, and therefore you can cut accurate parts. That's critical if you do very fine finishes. And then I would always recommend, if possible, invest in a small pellet system, so you can really run lights out. And doesn't have to be very sophisticated. You don't have to have a big setup, but maybe a little pellet pool where you can have 2, 3, 4, 5, maybe 10 parts run overnight. I would say that's a very useful option, certainly to have on the machine.
Okay. What is better, presetting tools for high-speed applications or using a laser tool measuring system that's in the machine?
I would say the laser tool measure is better in the machine. Sometimes you can also get like an optical measuring system on some machine tools. And the reason why I'm saying that is, specifically if you go into spindle speeds of like 40, 50,000, 60,000 RPM spindle speeds, what's going to happen, your bearing is going to open up for a couple of microns, and your spindle is going to drop by a couple of microns. And if you spin that tool at 40,000 and you measure that in the machine with your laser measuring system, you will have absolute data and you're going to be perfectly accurate. Versus if you do that in a preset station, you might going to lose a couple of a tenth or 2 or maybe more in that type of application. So if you're really looking for surface finish and accuracy, where it's critical that one tool knows exactly what the next offset is, I would recommend to have a laser tool measure in the machine tool.
Yeah, I think from a process efficiency standpoint, obviously you're not taking spindle time away by doing it offline, but for the precision, as Gisbert mentioned, as you're rotating the tool, you can check true length, true diameter in the cutting application, in the situation that you're cutting in, and you can also check for runouts. Vibration and runout are very, very critical. The faster you go, so being able to catch that and gauge it ahead of time will help the accuracy of the final result.
What are some of the typical spindle speeds that you're seeing in the high-speed machines these days?
I think we're starting out, we're going from 30 to 60,000. That's typically, we're starting at 30. That's what we consider high speed, and certainly then if you go to high performance, you're going down to 12 to 20,000. But high speed really, for me, starts at 30 to 60. We can go all the way to 90,000 if you machine ceramics, or you start a grinding process, then you can go all the way to air-driven spindles where you go to 100,000. But high speed, I would say between 30 and 50.
Mm-hmm. Depending on the application, of course, if you're doing titanium type materials, you want something with a lot of torque. Direct drive spindles, which are typical on these type of machines, aren't going to have as good a torque as a gearbox, but they will have better responsiveness and in our case, up to 500 foot-pounds of torque. And then they go all the way up to 30,000. As Gisbert mentioned, some of the air drive spindles. These are designed for really high precision, great surface finish, but again, they don't have a lot of torque, so it's something that needs to be looked at specific to the type of work you're going after.
Okay. You talked about the importance of CAM systems. Can you address how probing happens in settings like this?
There is just one company comes to mind here. M&H probing, for example. You can now, since machine tools are very accurate because they cut accurate. You can have a probing system on your machine. You can have the probe in your tool changer, and you can actually now load the print and the dimensions into your control, and then the probing system will compare the data the machine is measuring to your print actual data and give you any type of deviation. So before you take the part out, or if you have to make some small adjustments, there are probing systems out there, probably from Renishaw and others, who can provide you that information. And our own experience shows that since the machines are so accurate, you have linear glass scales, you have a thermocontrolled base, the machines are now really repeating and measuring as close as almost like a good CMM these days, within a couple of microns of repeatability. So specifically 5-axis, since you have the part in there, you can really reach all sides. You can, without a lot of setup, you can really probe the part in the machine and get really good results, and you know exactly if the part is sellable or not.
And keep in mind also, as we touched on earlier, the probe is part of the system that actually finds the true center of rotation of the machine. So a good, accurate, repeatable probe is the first step in an accurate result. There's two styles of probes out there. The more conventional historic probe has a physical trigger, a mechanical trigger. As you put pressure on the stylus, it'll break a spring-loaded ball, and that's what sends a signal back to the control. There are probes nowadays that have strain gauges internal. The strain gauge is more accurate, more repeatable. And as we get into more of the machine calibration, we tend to recommend that as a good starting point. Not a lot of difference in price in the probe itself, but it'll give you a little more repeatable, accurate result.
Very good. Well, Gisbert, Bill, thank you very much. And we want to thank our audience for joining us as well today. As you exit the screen, there is an opportunity for you to provide feedback for us. We would appreciate that. It helps us to continue to provide a quality product for you. And as well, you could make any recommendations that you'd like for upcoming future webinar topics. So again, the contact information for Bill and Gisbert is on the screen for you. And these guys are this is what they do, and they're a fantastic resource for you. Any questions you have, I'm certain they'll be able to answer for you. Thanks, Bill and Gisbert, and thank you all for joining us today. Have a wonderful afternoon.
Thank you, everyone.
Thank you. Bye-bye.